Hi, everyone. We'll start now. I'd like to welcome everyone to the fourth workshop on Bayesian deep learning. I'm Eric Nalesnik, and on behalf of the other organizers, I'd like to thank you for coming. We have a great lineup of invited speakers and panelists, and also 8 contributed talks and 100 posters. And then just some brief announcements before our first speaker. Full papers are now available on the workshop website. All posters will be presented at all sessions, so as I see some people are already doing now, please feel free to hang your posters at any time. Try to leave no more than 1 meter on either side of the posters so we can make sure to fit everyone. And then the workshop will end at around 6 p.m., a little earlier than what's listed on the website. And so with that, I'd like to welcome our first speaker of the day, Alex Matthews. He's a research scientist at DeepMind, and he'll be talking about the Gaussian process behavior of Bayesian neural networks.
Morning, everyone. Thank you for getting up bright and early. It's lovely to see so many of you here. Okay, I'm going to speak about Gaussian process behavior in wide deep neural networks. Those of you who are familiar with this area will know that this paper has been around for almost 2 years now. Say again, sorry? This paper's been around for almost 2 years now, and so it's fun to talk about it now because there's been a lot of follow-up work, and we can put it in the context of what's happened since. I should also mention there's an extended version of this paper on arXiv, which includes a more general theory and more extensive experiments, and there's code to reproduce this. I'll share the slides as well so you can follow these links. Okay, these are the co-authors. Mark Rowland and I have since moved to DeepMind, and there's Jiri Hron and Richard Turner, Zubin Garamani. But really this work is mostly a product of the University of Cambridge. Okay, so I think we'll hear a lot about this through the day, the potential of Bayesian neural networks. So data efficiency is a serious problem, for instance, in deep reinforcement learning. Generalization in deep learning is still, I think, poorly understood, although there have been some improvements. And I think part of the potential of Bayesian deep learning is to reveal and critique the true model assumptions of deep learning. But priors on weights are typically very difficult to interpret. And if we don't understand our prior, then why do we expect good performance? So it's possible, for example, that we're doing good inference, but with a terrible prior, so we get bad results. You actually did a good job, but you didn't see good results because you chose the wrong prior. Okay, so in terms of wide networks, the seminal result in this area is from Radford Neal in 1994. And he showed that a single hidden layer, MLP, with k hidden units, if you appropriately scale the prior, and that means scaling the outgoing weights with variance 1 over k, as you take the limit of that thing, as k tends to infinity, then the vector f1, which is of size number of data points, converges in distribution to a multivariate normal with mean 0 and covariance C. The elements of that covariance matrix Cij are some form of Gaussian quadrature, which involves the data points and the non-linearity. And to prove this, this is an application of the standard multivariate central limit theorem. I'll come back to proofs later. Okay, so I actually wanted to talk about the central limit theorem. I know to many of you it will feel extremely familiar. But actually, I'd like to tease out that even in the very familiar one-dimensional central limit theorem, there are some subtleties. OK, so firstly, what does convergence in distribution mean? Well, it means that the random variable converges to convergence of its cumulative distribution function at all points where that CDF is continuous. So the central limit theorem says that if we consider a sequence of IID random variables with mean 0 and variance sigma squared, and take the standardized sum, where we take the sum and divide by root n, then as n tends to infinity, Sn converges in distribution to a normal with mean 0 and variance sigma squared. OK, and I mentioned some subtleties. So let's take an example. Consider an IID sequence of Rademacher random variables. That's just two possibilities, -1 or 1, both with probability a half. So that has mean 0 and variance 1. And therefore, we can define this Sn, as in the previous slide. And the central limit theorem says that this will converge in distribution to normal 0, 1 as n tends to infinity. The subtlety is that we can consider a lattice, a countable infinite lattice, which is this set A. And on this lattice, Sn will always lie on this lattice, whatever n is. So the probability that Sn is in this set is 1, however long you wait. Whereas this set has probability 0 under the normal distribution. So although we have convergence in distribution in this example, there are examples of events that don't converge. It's a subtlety. You have to be very careful with what convergence in distribution actually means. OK, but we don't want to talk about just a single random variable. We want to talk about a stochastic process, an infinite dimensional object. Now, I'm not going to be able to talk about that in great detail, but one reasonable definition of that thing converging in distribution is that all its finite dimensional marginal distributions converge in distribution. OK, now I'm going to state the results for multiple hidden layers. Again, we carefully scale the prior, and we have K1 and K2 now for two different hidden layers. And the weights coming out of those layers will have variance 1 over K1 and 1 over K2, respectively. So we have this vector F2, which is of length n, the number of data points that we feed through the network. And that now converges in distribution to normal with mean 0 and covariance C2. Now, C2 is another normal quadrature, but this time the normal quadrature that we take is defined in terms of the covariance of the previous layer. In that sense, it's a recursive kernel definition, and a similar property would hold for 3 or 4, or indeed any fixed number of hidden layers. OK. So we're not the first people to think in this area. In particular, Cho and Saw, back in 2009, came out with this kernel with a different motivation. And there's a bunch of really interesting work that came before. And then publicly available on the same day and accepted at the same conference was this Deep Neural Networks as Gaussian Processes paper. So I think you can't get really more simultaneous than that. And that's a good paper. I would encourage you to check that out as well. So what were our contributions? Well, we gave a rigorous general proof of the central limit theorem with more than one hidden layer. And then, of particular relevance to this workshop, we did an empirical comparison to finite but still wide Bayesian neural networks from the literature. So why would we expect there to be a central limit theorem here at all when we have multiple hidden layers? Well, I'm going to start with an intuition. So Radford Neal, as I've already mentioned, let's imagine feeding a single input data point through, and let's look at one of these F1 units. There will be a single random variable at that point, and each of those F1 units is going to converge to independent random normal variables. That will mean that the push forward through the non-linearity is also increasingly independent. And since F2 is a sum of increasingly independent terms, we might therefore expect that that converges to a normal distribution as well. Now, if we think about what's going to happen with multiple input data points, there is now a correlated normal vector at each F1, and the elements here correspond to the different input points. We push that forward through the nonlinearity, and F2, as a sum of increasingly independent vectors, converges to a normal vector. Now, why isn't that argument enough to be sure that the central limit theorem kicks in? Well, the F1 units in the sum are only independent when they have reached their own limit. But that's only true asymptotically. So the convergence may depend on the rate which this limit is achieved. And we'll see that a bit more when I talk through the proof in a bit more detail. First, though, some preliminaries for the careful proof. Firstly, we're going to need a condition on the nonlinearity, which we call the envelope property. That means basically we can draw a bounding linear envelope around any point on the nonlinearity. And if you think about that, you're going to need that, because if you push a random variable through an arbitrary nonlinearity, you may get something whose variance is not even defined. So this effectively stabilizes what you're allowed in the nonlinearity. We also have this concept of width functions, and that allows us to talk about the network as an infinite sequence, so an infinite sequence of networks, and it allows us to consider the possibility that the different hidden layers may grow at different rates. As long as they all end up tending to infinity, we can consider any of those possible limiting processes. Okay, so the formal statement of the theorem says that for all strictly increasing width functions and any countable input set, the distribution of the output of the network converges in distribution to a Gaussian process, and the covariance function is the one that I already showed you that was first discovered by Cho and Saul. We're going to sketch the proof. So we're going to proceed through the network by induction, starting closest to the data. At each layer, we can reduce the problem to the convergence of any finite linear projection of data in units. And we're going to prove convergence in distribution and certain moment bounds that we then propagate by induction. The proof of convergence in step 3 makes heavy use of an exchangeable central limit theorem from Blum et al. In 1958, which I'll talk about now. So to recap, an infinite sequence is exchangeable if any finite permutation of elements in the sequence leaves its distribution invariant. Now, there's this fundamental theorem from Bruno Di Finetti, which says that an infinite sequence of random variables is exchangeable if and only if it is IID conditioned on some random variable. So if we look at later layers in the network and we clamp the layer previous to it, then we'll get back the independence that we needed for the central limit theorem. So although we have a dependent central limit theorem, the type of dependence we have is exchangeability, which is tells you actually quite a lot about the central limit theorem. The theorem applies to triangular arrays. This allows you to change both the number of terms in the sum and the identity of the terms in the sum. And if 3 conditions hold, then you have convergence to a standard normal. Now, note in particular that the terms becoming increasingly independent is not sufficient to guarantee convergence to a normal. You actually need something slightly stronger, and that means you actually have to prove something. We can measure the empirical rate of convergence for 1 hidden layer, 2 hidden layers, 3 hidden layers using MMD. And as I mentioned, we can compare posterior inference between the infinite limit and a large but finite Bayesian neural network with the appropriate weight scaling. So I should say the experiments in the paper, because we compare against gold standard Hamiltonian Monte Carlo, that necessarily means that they are on relatively small data with low dimensionality. In some cases, the majority of cases that we considered, the agreement is very close. So for instance, this commonly used Snelson data set in the Gaussian process literature, I can't tell the difference between the Gaussian process and the 3 hidden layer 50-unit neural network. Okay, a question I've got a lot since I wrote this paper is, we weren't sure that this was a good thing, this convergence. And others have been very excited about this property. Maybe that makes the whole thing easier. So I'd like to say a bit about why we think it's not necessarily a good thing. So a general regression algorithm can be written in the following way. A is just going to be some computation. X star is the test input you're interested in. Capital X is your training inputs, and Y is your training outputs. So that's all regression methods. Kernel methods are a subset of all regression methods where we can write the prediction as an affine transformation of the output data points. So that's a restriction. And in particular, I think that limits the representation that you can learn because the way you depend on your output data is very limited. Deep Gaussian processes are not marginally Gaussian processes because they have finite constrictions in the middle. So I wanted to highlight this as a very practical way that's actually quite a long way along of extending your model beyond Gaussian processes in a non-parametric way. And you should check out recent work on that because it's gone quite far. I'd also like to talk about subsequent work very briefly. There are some brilliant papers that I've had to miss out, sorry. First thing to say is that convolutional neural networks got knocked off. They also converged to Gaussian processes in these 2 papers that were simultaneous at the next ICLR. And I'd also like to highlight the neural tangent kernel, which considers not just what happens for the initial distribution of a neural network, but what happens when you then apply gradient descent. And there's been a great deal of excitement in that area as well. But the neural tangent kernel is very closely related to this kernel that I mentioned in this talk. Okay, and then I'll maybe have time for 1 or 2 questions, although I'm quite close to the end, I think. 1 question.
If anyone wants to come up to the microphone.
Oh, we've got one.
Hi. So thanks for the talk. Super interesting. I had one particular question. In the plot where you showed that the Gaussian process looks a lot like the 50-unit neural network, you say that for all the training points, you get a really close matchup with the finite dimensional distributions. Do you believe that because there are only a finite number of basis functions, there exist points in the input space where the distributions for this example do actually differ quite a lot?
That sounds like a question which you might have an idea of the answer of. I haven't observed that, no. But I'd be happy to take it offline.
That is already very useful information. Thanks.
Let's thank the speaker. Let's use your, sorry, I don't have access to that email link.
What's next?
We're going to do Tim Rudner. Okay, we now have our first contributor talk of the day. That will be by Tim Rudner, who's a PhD student in Oxford, and we're talking about natural neural tangent kernels.
Great, thank you so much. Before I start, I'd like to thank the workshop organizers for giving me the opportunity to present this work. And so I will be presenting the natural neural tangent kernel, neural network train dynamics under natural gradient descent. And this is joint work with my collaborator, Florian Wenzel, and my advisors, Yi Tay and Dayan at the University of Oxford. I will first give a brief overview of some relevant background. Next, I will present our theoretical results and our empirical evaluation, and I will finally conclude with a few remarks on current and future research directions and potential application areas of this work. Following previous work, we vectorized the outputs of a neural network with k-dimensional outputs into a single n by k-dimensional vector, and we define a concatenated loss and likelihood accordingly. We note that in the application we have done so far, we're only looking at one-dimensional outputs, but all of our theoretical results apply to multidimensional outputs, such as multi-class labels as well. To understand our work, it is important to understand the recent related work on function space training dynamics of deep neural networks. Here, we will introduce the approach by Jacob et al., which was published at last year's NeurIPS. First, consider the parameter space dynamics as an evolution over time. In the first line, we simply state the gradient descent update rule as a time derivative, which is just a standard gradient update rule with a chain rule applied to the derivative of the loss, since the loss itself is a function of f, which in turn is a function of the parameters theta, with respect to which we would like to take the derivative. Now, moving to the evolution in function space over time, we note that the deep neural network outputs are a function of the parameters, which in turn are a function of time. We apply the chain rule again and get the derivative of f, the deep neural network output, with respect to theta times the time evolution over theta, which we just derived above. Putting these two together gives us an expression for the function space dynamics of deep neural networks during gradient descent training. However, so far we've only been considering the functions predictions at training time on training points, calligraphic x. Jacob et al. Noted, however, that the time evolution stated here can be interpreted as a kernel function, which defines a function over a function space over the training inputs. The kernel function, called the neural tangent kernel, however, can also be evaluated at a test and a training point to yield a prediction on a test point during training time or during evolution of gradient descent. This in turn gives us an expression for the predictions on a test point during gradient descent training, and we will come back to this formulation shortly. First, I will briefly introduce natural gradient descent. Natural gradient descent is appealing because it has several appealing properties, including fast convergence and invariance under reparameterization. Natural gradient descent is like gradient descent, but with a preconditioner matrix multiplied to the loss derivative. This preconditioner is the inverse Fisher matrix, Fisher information matrix, and with it pre-multiplied, we almost get the same parameter space evolution as for gradient descent, as can be seen here. One way to understand the impact of this preconditioner is to note that the inverse Fisher information matrix, the Fisher information matrix allows gradient descent to take the curvature of the distribution distribution space into account. This means that small changes in the parameters can have a big impact on the neural network outputs, and performing gradient descent does not take into consideration how the output changes when updating the parameters. The inverse Fisher, however, does exactly that and allows natural gradient descent to move along this curve in distribution space by taking into account the space's information geometry. Now, a final note on the Fisher information matrix. For deep neural networks, we can define the Fisher information conditional on x and then take the expectation over the empirical data distribution. which, after applying the chain rule, leads to the empirical Fisher information matrix given in equation 8. Furthermore, for a Gaussian likelihood, this Fisher information matrix simplifies further, giving the expression you see in equation 9. And this is what we will be using going forward. Now we're ready to talk about natural gradient descent in function space. To recap, the same way we can derive the function space representation of the train dynamics under gradient descent, we can derive the function space train dynamics under natural gradient descent, where we follow the same steps as before, as you can see here, and end up with an alternate kernel, the natural neural tangent kernel, which includes the Fisher information matrix between the two gradients. That's what you can see in equation 13. Now, before we move on, we need to make two relatively mild assumptions. First, we assume that we're dealing with an overparameterized deep neural network. That is, the number of data points times the output dimensions k is less than the parameters of the neural network p. Second, we assume that the gram matrix, given here as G, is positive definite. It is worth stressing that we do not assume that the neural network is infinitely wide. We only assume that there are more parameters than data points times output dimensions. Now with that, we can return to the natural neural tangent kernel. Since p is greater than the number of data points times output points, the p by p Fisher matrix is surely singular, which requires the use of a generalized inverse, which in turn requires that the gram matrix is invertible, hence assumption 2 on the previous slide. Computing the natural tangent kernel on the training points then yields a somewhat potentially surprising result. Since the different gradient terms cancel out, we're left with an NTK that's constant in x and t. It's just a scaled identity. Revisiting the function space dynamics on the training points, we then see that the differential equation at the top has simplified significantly and becomes linear under MSE loss, which allows us to solve the train dynamics analytically, as we can see in equation 20. However, this is not really what we want. Since we're interested in predictions on arbitrary test points, not just on training points, which we required in the previous derivation. If we wish to make predictions on an arbitrary test point, see now equation 21 and 22, the dynamics become intractable again, because we do not get the same cancellation. To be able to solve the dynamics regardless, we follow previous work by Lee et al. And make a linearization assumption that the neural network parameters evolve linearly from initialization, which in turn allows us to solve the dynamics analytically. And the solution to those dynamics is given in equation 24. However, you might ask, why would we want to do this, and how is this different from previous work? To answer this question, we point out that due to the fact that the function space training dynamics are linear in f on the training points, we can show that the evolution over training points under the linearized model and the non-linearized model are in fact the same. This is what's shown in equation 26. Now, this insight in turn allows us to derive a bound on the discrepancy between the predictions from the solution to the linearized dynamics model and the non-linearized dynamics. The big difference the identity above makes when writing out this discrepancy is that a complicated term, here denoted as a function c, dependent on the difference in f and the linearized f, is 0. Additionally, the functional form, I apologize, the difference in g, where we define g as the difference between f and the test labels. However, this discrepancy has the test labels cancel out, so in effect you get f-lin minus f, the predictions from the non-linearized dynamics. Additionally, the functional form of the natural NTK allows us to derive a much tighter bound than would be possible for the regular NTK. But to see the details of that, I recommend looking at the proof, where we show that the bound above only follows for the natural NTK. Taking a step back, though, what have we shown here? We're able to give a bound, which we argue is relatively tight in practice, that tells us how close our predictions are from the analytical solution. Our predictions from the analytical solution are to the predictions from just running natural gradient descent, or what you could call the true solutions. Crucially, we do not require an infinite width assumption or any other major assumption on the training dynamics of the neural network, apart from the linearization, which we argue is relatively justified empirically and because of the linear evolution on the training points. To test the main theoretical result, the bound that I just presented, we considered a simple synthetic data experiment. In this figure, we plot the predictive distribution of the analytical solution obtained from multiple random initializations, as well as the theoretical bound, which are the blue lines around it. As you can see, the theoretical bound is relatively tight, and in fact includes most function draws. If you look at the values of the discrepancy bound, i.e. the actual values that follow from this bound, you actually see that the values increase further away from the data, even though they only increase slightly. So the values on the very left and the very right are larger than the values in the center. Additionally, comparing the predicted distribution from performing gradient descent until convergence for several random initializations shows that the uncertainty estimates under the solution to the linearized dynamics are far superior. They collapse around the data and are far away from it. The same applies if we use regularization techniques such as dropout when training the neural network. Oh, this is an error. One of these should show dropout, which showed uncertainty that does not collapse around the training data, and the mean underfit the data, given that we're only predicting the neural network on a relatively small data set here. If you want to see the full plots, I refer you to the paper. Lastly, we also evaluated the test accuracy on real-world benchmark regression problems. While it would be unwise to read too much into this specific evaluation, we see that, somewhat surprisingly, the solution to the linearized training dynamics yields a lower test RMSE on very small data sets than the predictions from a neural network trained with gradient descent until convergence. Finally, future directions and applications. We're currently working on a few directions, including establishing a link between the linearized training dynamics under random initialization and approximate inference, and extending the approach to stochastic gradient descent to make it more scalable. Other potential fruitful directions we're exploring are deriving a proper generalization analysis and extending our experimental results to classification tasks. In terms of potential applications, two immediate applications of this work would be to use the parameter space predictions obtained from the analytic solution as a smart initialization for example, approximate natural gradient methods such as KFAC, or to use the function space predictions as a prior for functional variational inference. Thank you. I look forward to taking your questions and speaking to you at the poster. Do we have time for questions? Yeah. If there's anyone. Any questions? Okay, come find me at the poster.
Thanks, Tim. Okay. Our next invited talk will be by In-Jin Lee, research scientist at Microsoft Research Cambridge. And she'll be talking.
So this is not showing out yet. Let's wait.
There we go. Yeah, and she'll be talking about on estimating epistemic uncertainty.
Hi, everyone. So welcome to this workshop that early. And so today I'm going to tell you a bit about my thoughts on estimating epistemic uncertainty in a little bit retrospective way. So because for me, like breakfast is not like equation time, so I try to make this talk quite high level. So I will push the technical details into like just a few slides. So if you have questions, come to the poster and we can also chat in person. Okay, so I consider myself as a Bayesian person, and my main community is approximate inference and also Bayesian deep learning. So I attend this workshop for quite some time, and finally I can stand here to give you a talk. So on Sundays, the approximate Bayesian inference workshop is kind of like a big party of like approximate inference and also Bayesian believers. So we are super happy, and we discuss tons of like advanced approximate inference and also sampling methods in that workshop. So everyone is happy, but in the panel session, so I feel like the panel session is a little bit pessimistic. So I remember one question in the panel session saying that, okay, so we are doing very good Bayesian modelings and we are happy, but how we can make like the general NeurIPS community to actually care about what we are doing, right? So yeah, that is definitely a question that we need to consider. But so after that day, on Monday, so MTCAN gave a really good tutorial on Bayesian deep learning, and you can basically see that many people actually show up with curious heads. So I think that because uncertainty estimation is actually a very important problem if we want to apply deep learning methods to critical areas that has high risks. So if we can make progress on like uncertainty estimation methods either in the Bayesian way or non-Bayesian way, then we have really great potential to extend machine learning methods to like say autonomous driving or healthcare applications. Okay, so that's my observation, and let's see what's going on here. So I'm going to try to set up the background and try to make sure that everyone is on the same page by starting talking about the type of uncertainty. So let's just give you an example of flipping a coin. So you get a coin and then flip it a few times, and then you want to know whether this coin is fair or not. So epistemic uncertainty is basically your internal belief after you do a bunch of experiments saying, okay, how much do I believe this coin is fair? So this is, your belief after a few observations, and your belief can be more and more confident and certain when you do more and more experiments. Okay? So that's epistemic uncertainty. The aleatory one deals with the inherent randomness in the data generation process. So, I mean, even when you are very certain about this coin is fair or not, then you can still not predict like the next outcome of the next experiment. So this is regarding the uncertainty in individual experiment outcome, and this is non-reducible. So one thing that is related to epistemic uncertainty, but I still want to point it out, is distribution shift, and I believe there will be another amazing invited talk about this. So this is about like the scenario where when you flip the coin, actually the coin is not in your hand, so another one gives you a coin, and then this time you actually need to infer whether you are still flipping the same coin. Right? So this indicates like the changes of the underlying quantity of interest. So this applies to, say, out of distribution detection and also distribution shift. Right. So I've talked about the type of uncertainty. So let's basically just go into the details of like how this uncertainty estimation in neural network works. And in particular, because I'm Bayesian, I'm going to do Bayesian neural networks. So this is a super quick introduction of Bayesian neural networks. So let's say you are going to classify different types of cats. Usually people, build neural networks by, parameterizing the neural network with some weights, and then put a softmax layer on top of that to predict the kind of probability of each classes. So the Bayesian solution says that, okay, instead of putting a point estimate, or you learn these weights with gradient descent, we are going to put a prior distribution on the weights. And then after you observe the data, we are going to follow the Bayesian principle and then compute the posterior distribution of the weights given the data. So this is just basically Bayes' rule, okay? So once you've done the Bayes' rule, and in the prediction time, we can do this kind of Bayesian averaging by saying that I'm going to average my solution, my prediction of the new data, from the weights of the posterior. So this is what we do in theory. But in practice, so we cannot compute the exact posterior in the exact way. So this is basically just the biggest challenge of Bayesian inference. So what people do in practice is to first find a simpler approximation distribution Q that somehow approximates the exact posterior well. So the methods include live version inference or MCMC. They are essentially doing the same thing. So in prediction time, once you've got this approximate distribution, then you can basically, say, sample a bunch of weights from the approximate posterior, and then ensemble your solutions to predict the Y outcome given the new input. So this is the setup of how actually Bayesian neural networks works in practice. Okay? So I've talked about we want to estimate uncertainty, right? So from the previous slide, we are going to build approximate posterior in the weight space. But to me, the weight space uncertainty is actually less interesting to me. So there are a few reasons I just give you two. So in many cases, neural network parameters are somewhat randomly parameterized. They are actually not the scientific parameters that we are interested in. So for example, if you are doing some sort of physics experiment, maybe you are actually interested in is the kind of the underlying parameters in your physics simulator, which is not expressed by neural network parameters. Okay? So that's the first reason. And the second reason is, neural networks, they have a lot of redundancies in the sense that they are kind of have a lot of symmetries there. So I just show you some examples here because you can see that by swapping the node or made the kind of the weights scale up and scale down in the next layer, essentially you are parameterizing the same function. Okay, so this basically means if your approximate posterior is capturing this kind of symmetries, then in function space, you're still getting pretty much the same function outputs, which is less interesting. So I already alluded to my preference on capturing the uncertainty in function space. Okay, so let's see how actually it works in Bayesian neural networks. Because neural network functions are parameterized by weights. So that basically means that if you sample a weight from the Q distribution, then this is equivalent to sample a function from some sort of Q distribution in function space, right? Although this Q distribution in function space might not be GP. Okay, so when people try to kind of evaluate the uncertainty in function space, so there is actually a folklore belief where I also believe as well, which says epistemic uncertainty should be high when new input is less similar to observed input. So here I'm showing you a quite famous example from Miguel's 2015 SCMR paper. So this is a regression example that in the Bayesian neural network literature people often use to basically just show the qualitatively the quality of their uncertainty estimate. Okay. So I'm showing you different methods. You can basically see that some methods actually do give you higher uncertainty when the input is less similar to observed data point. But the question here is essentially, so what do high uncertainty and less similar mean quantitatively, right? So often when people look at these papers, including myself, we do eyeballing, which is actually a subjective evaluation, and different people have different beliefs on on the preference on what kind of uncertainty they should look like. So in the literature, I believe at least for this example, there is really no say a agreed description on where you should be high and how much you should be high. Okay, so. So that's a very difficult problem because if you talk to a Bayesian people who believe subjective Bayesian, then epistemic uncertainty is actually quite subjective. But for me, because I'm an approximate inference person, I would still like to evaluate the accuracy of my approximate inference method. And actually, in approximate inference literature, you do have a target that you can target for because approximate inference, you do have this kind of goal to approximate the exact posterior. So that basically means, okay, if I do have the exact posterior, then I can evaluate the quality of my approximate inference. But the problem, as I already told you, the Bayesian neural network weights, they are super complicated. I presume the posterior of the Bayesian Bayesian neural networks in weight space have multimodes because of this kind of symmetry stuff. So that basically means we don't really have that. And even we don't have a robust way to estimate the moments for the posterior distribution in weight space. So it seems like we are doomed, right? But as I said before, what I care is actually the uncertainty quality in function space. So previously, we have very little hope for evaluating approximate inference methods in weight space, but we have some hope in the function space. So Alex just gave a fantastic talk telling you that, okay, if you make some assumption on your Bayesian neural network prior, and then make your network wide enough, so then you have this kind of GP limit for the Bayesian neural network prior, right? And that also gives you the posterior distribution for that corresponding GP. And you know, in the regression problem, GP posterior actually has an analytical solution, which is a Gaussian with some sort of mean and variance, right? So that basically means, at least in the small data region and the regression problem, we do have some sort of reference in the function space. So that's basically what I'm trying to compare with. So I'm trying to compare with my kind of, say, approximate posterior approximation in the function space to like this kind of GP limits. I mean, so this is not a comparison to the exact posterior because I don't have that, but I'm just using it as a reference to basically see how well we are doing, at least in the first 2 moments. Okay, so we are going to present a poster this session. So I'm going to tell you a bit about like some summary of the result. If you're interested in the kind of like the details, come to the poster. So in this case, we're interested in something called in-between uncertainty, which basically says that if your data comes in clusters, so you have gaps, or you have, say, unobserved points in the between of the clusters, then we still want to estimate the uncertainty in between that, right? So this applies to, say, time series data when you have, say, missing values, and also like, say, clustering or classification when you have ambiguous input. Okay, so just tell you a bit about the result we have for Bayesian neural network regression. So we are considering this kind of, say, mean field Gaussian approximation stuff. And so we want to understand like how well this is actually working in the function space. So, you know, for approximate inference algorithm, there are actually 2 components. First, you actually need to define like the class of Q distributions that you are going to find your optimal solution in. So one question that we need to address is whether this, you know, approximate inference Q family is flexible enough. So we did some sort of mathematics, and then we figured out that in the one hidden layer case, the approximate, if you use mean field Gaussian approximation, then there is actually some sort of theoretical limitations that you cannot achieve. And this actually applies to any approximate inference method, not only the variational inference method. Okay, so this sounds like bad news. But then we also extend our kind of analysis in like deeper neural networks, and you know, people hope that when you cannot do things with shallow networks, then try deeper networks, right? So we also try something on that. So we have some good news and bad news. So we have a constructive proof to show that, okay, if you only care about the mean function and the variance function in the output space, then you can basically, you know, use deep neural networks to find out like the favorite mean function and variance function you like, right? So that basically tells you that the mean field family is somewhat, you know, expressive enough to capture the uncertainty you like. But the problem here is, okay, so the family is expressive enough, but can you actually recover the answer in practice? So that tells you, okay, we need to you know, think about the algorithm and also the optimization algorithm as well. So we try very hard. We try different tricks to basically, you know, help mitigate problems, for example, like in initialization or also like in objective function. And also we compare our results with kind of like the previous GP limit reference. So what we found is that at least for the experiments we have up to date, we didn't manage to kind of close the gap between the variational inference result and also the GP limit results. We should try harder and tell you like the final outcome, but you know, I think in order to find it out, we probably need, say, better theoretical tools or like better optimization tools to actually show that in practice. Okay, so that is kind of like good news and bad news for this research. But now the question here is, as I tell you, like for subjective Bayesians, the kind of like the uncertainty, epistemic uncertainty is subjective. So then, because when we use this kind of GP limit thing, and in the GP limit thing, we also need to define a prior, which is, chosen to basically just make sure that these GP things works. So someone may argue that, your GP posterior inference reference is also subjective, right? So I buy that because, so if you don't do this kind of, say, empirical based or objective based, then everyone can blame this point. So let me tell you what is happening now in the practice for Bayesian neural network selection. So first, because Bayesian neural networks, we need to do approximation. So in practice, we actually select model and inference together. And interesting enough, so we never try different inference techniques, and only try only once, and then determine whether our model plus inference is good or bad. And second, the way we select different Bayesian neural networks is based on the statistics of total uncertainty, or some kind of balance between aleatory uncertainty and epistemic uncertainty. And the third thing, which I admit I also did this before, is that we only look at average metrics for those uncertainty values, uncertainty metrics. So we kind of ignore the fact that some test examples can be different from training ones in very different ways. So we don't only get an average answer and just ignoring this part. Okay, so now we've done this selection. So in practice, because we are actually selecting inference and model together, so that basically means good performance in practice can come from possibly two cases. One, a good model with close to exact inference, and another, a bad model with bad approximate inference. So for example, let's say your exact inference is super underconfident because your model is bad. Variational inference usually gives you, say, a confidence result, so that gives you corrections. So and the final results is okay, right? Okay, so it seems like, okay, if we only care about practical performance, then maybe selecting the second case is okay, right? So I'm trying to understand whether this is really okay in practice, so I came up with this example. So suppose you start from a very bad model, and then you observe your first task, and then do approximate inference. So somehow, your bad model equipped with bad inference gives you some good performance in practice. Okay, I buy that for the first task. And then we are going to do, say, online Bayesian inference, and then come with the second task, which is actually similar to the first task. So if you follow the kind of Bayesian principle, this tells you that, okay, I'm going to use the Q distribution in the first case as the prior for the second one, and then do similar Bayesian or approximate Bayesian inference procedure on that. So now you've got a new approximate posterior Q2 of W. So the question now I'm trying to ask is that, do we still expect good practical performance from Q2? Because in this case, you have bad inference, right? So I will still think about this problem, and I will leave you to think about this problem. So just to summarize what I've talked about, so I've tell you about some thoughts on the evaluating epistemic uncertainty and gives you some example. So these are kind of like research I've loved to do and I've loved to see in the future research. So as an approximate inference, I still want to improve approximate inference methods and try to understand the gap between the approximate inference method right now and also some reference we want to achieve. And also, I want to, encourage people to think about better description on what we really want from modeling uncertainty. For example, I would like to see some sort of, say, evaluation of the uncertainty methods on data subgroups, maybe because, you have, say, in medical center, you have different patients, every patient are very different. So thanks, I will take questions.
Thanks for a really interesting talk. So I just want to be sure I understand. You were saying that you have a theoretical result that says that in the two-layer case, mean field VI, if you could only find the best approximation, would be good. Is that accurate?
So okay, so here's the statement. So first, you need to think about whether you only care about mean function and variance function. I haven't even said anything about covariance function. Okay. So second, what we are trying to do here is to build a constructive proof to tell you that there are at least exists some sort of ways to construct the neural networks Q distribution mean and variance so that you can achieve the mean function and the variance function you want.
Okay, very interesting. Thanks. I just wanted to make sure that I had that right.
So thank you for the talk. Just first a comment about that. We have some interesting results looking at convergence, so looking at the expressivity of deep MFVI as the depth increases, and looking specifically at the variance, showing that MFVI actually becomes better and better approximation, which is quite surprising. What I actually wanted to ask about was, what are you trying to compare here? Are you trying to compare the uncertainty, or are you trying to compare the, sorry, are you trying to compare the uncertainty from the model or from the approximate inference? Because if you're trying to compare that from the model, I would probably look at HMC, not at GPs, because we know that the limit when you take the GP actually throws away a lot of properties, and like actually you would have very different properties for the uncertainty. So I wouldn't use that as the gold standard in that sense. But if you try to compare the approximate inference uncertainty, I wouldn't necessarily, we do have benchmarks to look at whether the uncertainty is actually useful. So like you mentioned that we need benchmarks in the field. There's been stuff that we've done, there's stuff that guys from Google done that we're going to talk about later today as well. There are a bunch of really good benchmarks in the field by now to tell whether your uncertainty is good or not, going well beyond just 1D regression tasks.
I totally understand, like, I mean, I should say that, okay, in practice, evaluating uncertainty is definitely model plus inference. So what I'm interested in here, so I would say that this result is only comparing inference. So I also agree that HMC is like, say, gold standard, but the problem here is essentially, you know, HMC, when you make deep neural networks, we still need to figure out like when it actually converges. So, I mean, so in this case, I never claim that this GP limit is the exact posterior. So this is, okay, where is that? Yes, I'm only using this as a reference. So I agree that there is a gap between this reference and the exact posterior. But as I said before, what I'm interested in is in the function space behavior. And in the regression case, we mostly care about mean function and the variance function, and that's why we decide to use GP references. If we can make HMC work, I would love to see HMC work and actually compare to HMC.
Okay, so that's really good. So like, interesting direction for researchers is to actually get good tools to get HMC to be more robust, basically, to get it to be much easier to work on.
Yeah, I completely agree. We should definitely work on sampling methods for neural networks. In fact, I've also tried, say, some sort of HGMCMC methods and try to make it work. But, you know, like in practice, HGHMC or this kind of, say, optimization-based sampling methods also has problems. And I would kind of want to, say, borrow some ideas from the optimization community to actually address that.
Thank you.
Sorry, we don't have time for any questions. Please take it offline. But let's thank the speaker one more time. Our next contributed talk is by Stanislav Fort. He's an AI resident at Google Research and also at Stanford now. And he'll be talking to us about deep ensembles, a lost landscape perspective.
Good morning, everyone. My name is Stanislav Fort. I'm a PhD student at Stanford University, and I'll be presenting my new paper called Deep Ensembles, a Lost Landscape Perspective, which I did during my AI residency in Google Research last year, together with my amazing collaborators, Clara Huey Hu and Balaji Lakshminarayan from DeepMind. The fundamental question we're trying to address is a simple observation that scalable Bayesian methods do not seem to be, in practice, capable of outperforming simple randomly initialized neural networks which are trained with random batches. We're trying to address the reason for why this could be the case despite the superior guarantees we have for Bayesian inference in small number of dimensions. Our hypothesis is that due to the structure of the lost landscape, Bayesian methods in particular have a hard time traversing multiple modes and essentially get stuck in a single mode despite our best efforts to prevent so. I'll just introduce the problem in general. So we feed an image, a data point here represented by a cute turtle, into a neural network which is a function parameterized by a weight vector W, which then produces a vector of probabilities P, which then compared to a ground truth solution produces the loss L. We will be dealing with two notions of distance in our problem. The first one is the weight space distance, for which we will be dealing with a function called the loss landscape, in which we look at how the loss, characterized by the L, depends on the W vector, W. That vector is a high-dimensional vector, so we can imagine this function, the loss landscape, to be a high-dimensional loss landscape in which we get hills and valleys, and we're trying to navigate it using SGD when we're looking for a solution. In particular, we'll be studying the weight space cosine similarity, which is a notion of distance between two weight vectors. And in this graphics, it is an angle between the solution 1 and solution 2 vectors corresponding to particular points in the weight space. And in particular, we'll be looking at the theta between them and their cosine. For random vectors in a high D space, the cosine is expected to be roughly 0 with small deviations, scaling with 1 over the square root of dimension for high dimensions. When we look at actual runs, actual experiments, we notice that orthogonal vectors result from random initializations being trained with random batches. And within a single run, we notice that the cosine similarity between weight vectors during epochs is very high, meaning that they move roughly parallel in a radial direction in the weight space. The other similarity notion we'll be dealing with is the function space similarity, which in general is really hard to evaluate because the input to the neural network is a high-dimensional real-valued space. What we do is sample this distance on the test set, so looking at how predictions between the test set between different functions differ. We choose a simple metric that is intuitively understandable, and that metric is only what I show on the slide. It is the difference between the predictions on the test set between two functions, function parameterized by W1 and the other function parameterized by W2. We look at the average, we look at a fraction of labels on which these functions disagree. We call this notion diversity of solutions. And we notice that between randomly initialized solutions, randomly initialized and trained solutions, we get very diverse solutions, roughly equal diversity between any pair of solutions, apart from the solution itself, which has a 0 diversity with itself. And then within a single run, the solutions are very similar to each other as the epochs progress in the training. So within a single run, we notice similar solutions appear. Within different runs, they're as different as it's possible between every individual pair. On this graphic, I show a t-SNE plot in the prediction space, meaning that we take the predictions on the test set and look at the predictions along epochs for 3 different runs, a red initialization, a blue initialization, and a green initialization. In the GIF on the right-hand side, you can see how these runs move out in the radial direction, sticking close together within the single run, but being very different from each other between the runs. This shows that the individual runs within each other, within themselves are similar to each other in predictions, but between each other, they are quite different. We will now be studying how subspace sampling methods in the neighborhood of a solution look like in the prediction plane in the t-SNE plot. We try 4 different sampling methods, the first one being the basic one in which we randomly sample the weight space coordinates around a particular solution, the second one being a simple diagonal Gaussian, the third one being a low-rank Gaussian, and a fourth one being a Monte Carlo dropout. These provide a set of solutions in the neighborhood of a particular weight space position, which is the final position of a certain run, let's say after 100 epochs. And we visualize how the predictions in these subspaces compare to the individual runs. Let's wait until epoch 60 when I start showing the positions, the predictions of these sampled functions. You notice that the functions stay near the original solution from which they were sampled. So we never traverse the gap between the individual runs using these subspace sampling methods. This is a t-SNE plot, so it could be misleading, so we wanted to quantify, in particular, what exactly happens quantitatively. These are 4 plots for 4 different random sampling methods. The first one is the random subspace method, the second one is the dropout method, and the 2 normal sampling methods are presented in the bottom row. You see that the clusters of the lighter color next to the high hue runs are in general within the neighborhood of the individual runs, meaning that the functions we sample in the function space never deviate much from the original solution. To quantify this, we looked at what we call diversity accuracy plane. We would be plotting the test accuracy of solution and on the x-axis, and then on the y-axis, a notion of diversity, which is the fraction of labels on which two solutions disagree on a test set. We have a referred solution, which is the green star, which is an accuracy of 90% in this particular case, and a zero diversity because it is the same as itself, so we are comparing to that particular solution. Then we put on this plot 10 other randomly initialized and optimized solutions, and you notice that they have a roughly equal diversity on the y-axis while having roughly the same accuracy as the reference solution, so 90%. You can notice that they cluster together, so all of them have a roughly equal distance in diversity to the reference solution. This curve is now the minimum curve we can imagine being conceivable in that plot, being a random deviation from the reference solution by random perturbations. So the solutions we obtain on this curve are highly correlated with the original reference solution. The upper limit is the exact opposite, where the solutions are completely decorrelated. So any particular sample will lie in between these two curves. When we start sampling in a subspace around a particular solution, in this case the green solution, we notice that we're exchanging diversity and accuracy in a certain way, marking a crescent on this plot. We see that to obtain a higher diversity, we need to exchange more accuracy using these subspace sampling methods than we would normally get when we initialized again and optimized again. The same holds true for different sampling methods, such as dropout, simple Gaussian, or rank for Gaussian. Notice that the cluster of independent solutions is an independent cluster that's not reached by these subspace sampling methods. That means that the exchange of diversity for accuracy in this particular case is better than for the subspace sampling methods as we observed. This seems to be true even for bigger models. For example, on the left-hand side, ResNet 20 on CFAR10 and ResNet 20 on CFAR100, reaching not exactly state-of-the-art performance, but quite close to it. It seems to be the case that the more difficult the model, the better this notion of separation between the ensemble group, the red stars, and the subspace group holds. When we study the loss landscape and try to sample from it, what we could do is we could sample, So we can imagine the loss landscape, there exist different modes. On the left-hand side being depicted by the green color, being the accuracy of the solution. These modes are in fact connected, as was observed this year in multiple papers. However, on the random slices they look disconnected. However, despite their same loss, their functions are distinct, as indicated on the right-hand side with the red and blue functions. We don't have to rely on toy models. These are real slices of the loss landscape, which are equivalent to what I showed you right here. On the left-hand side, being a loss between two solutions, or accuracy in this case in particular, and on the right-hand side showing the similarity to two reference functions, the blue dot being the blue function, the red dot being the red function. So those are the real versions of the cartoons I showed you before. Because the modes touch in real life, we can traverse them using optimized connectors, as has been realized in multiple previous papers. We would assume Bayesian methods could traverse these connectors between modes and therefore sample diverse set of functions. However, in practice, it doesn't seem to be that easy. When we're looking at ensembling in the weight space, what we could do is we can run weight averaging on the individual modes. That would mean doing the blue dots in the blue cluster and the purple dots in the purple cluster, and then getting a star solution, which is the average solution in the weight space, which lies in the convex hull of the weight vectors of the individual samples. This, however, would provide a limited diversity because we have to stay within the same cluster. We could do the normal ensembling in which we take a sample from each mode, independently initialized and independently optimized to, and then average the predictions. However, we can get both. We can get the best of both worlds by first doing weight averaging in the individual modes and averaging the predictions of those average predictions. This, as we verified on ImageNet, provides both superior accuracy as well as calibration measures. I think we should view these observations as an invitation to design Bayesian methods that explicitly use the new insights about the lost landscape of neural networks that have been collected in the past 2 years. I think the fact that the modes in the loss landscape are connected provides a unique opportunity and a proof that we can actually sample multiple modes using Bayesian subspace sampling methods. However, it seems to be hard doing that using the priors we currently use. So I would view this as an invitation to design better methods that are more tailored to the specific nature of the loss landscape of over-parameterized neural networks that we have been observing this year. I think the takeaways from this paper are that scalable subspace variational sampling methods primarily explore a single mode, which we verify by observing the diversity accuracy plot and exchanges between diversity and accuracy for different subspace sampling methods. I think we should be using the explicit geometrical structure of the loss landscape to design better Bayesian methods that realize the full potential of the technique. I think by combining local weight averaging and global ensembling, we can get the best of both worlds. And that's a practical method people have been using already. Thank you very much.
We have time for some questions, but while that happens, can the spotlight presenters come up to the stage, please?
Thanks for really interesting work. I feel a little bad asking this because you did such a thorough set of experiments, and I'm going to ask you, what would happen if you did one more experiment? But I'll ask anyway. So, I guess one hypothesis that you could imagine being true, I'm not saying I think it's true, but I'm curious, is that there's enough symmetry in these neural networks that accurate sampling within one of these modes, if that's the right word for them given that they're connected, that accurate sampling of the posterior within one of these modes would be adequate because maybe they all look the same. Do you have any experimental results that sort of speak to that, right? So as opposed to this trying to find sort of the center of a mode and then averaging those things, right, or averaging across all of the modes, if you just did an accurate job of sampling within a mode, do you have a sense for how that would compare, or is, because these subspace methods, right? I don't think it's not obvious that they're doing an accurate job of sampling even within a mode.
Mm-hmm. I think the experimental evidence suggests that they in fact do find a better optimum within the mode. Was the question for why the individual sample isn't as good as the total, or?
The question is, and maybe this is something you just don't have evidence for yet, but right. So if your mental model is there are these different modes that are just that are hard to it's hard to get from one to another. It could still be the case that accurately sampling within one of those modes, right? If you just restricted the posterior to one of those modes, that accurately ensembling samples from within one of those modes would give you results that were as good or almost as good as sampling across multiple modes.
I see. That is certainly conceivable, and I believe maybe some really complicated Bayesian methods could do that. However, all the experimental evidence we see suggests otherwise. We think the actual diversity is only, at least in our experiments, all empirically bound to our experiments, only appears when we actually sample from discrete modes that we obtain by independent initializations and optimizing to them. We haven't seen a case where the single mode would perform as well as the full ensemble of modes. Okay. But it's an empirical observation.
Yeah, that's great. Thank you.
Thank you.
Thank you. We'll now be having our 15 poster spotlights.
Hey. Hello, everybody. So I'm Angelos. I'm going to present today our work on systematic comparison of BDL robustness in diabetic retinopathy tasks. So this is work in collaboration with a few people from Yarn and Oxford. So in short, we're proposing this tool, which is a set of new real-world benchmarks for BDL that highlight the importance of quantification of uncertainty in real-world domains. And in particular, today, we're going to build on a previous paper coming up on Nature Scientific Reports from Laban and Company, which is on building on diabetic retinopathy images. So in particular, on the right-hand side, we can see some examples from some retinas of diseased and healthy clients and patients. And what we have is that we use probabilistic models to identify the certainty about the different patients. And given that we are certain enough, we can follow the necessary steps to accommodate the needs of the patient. Otherwise, we're sending them to experts to follow up on that. So briefly, we have some baselines that we compare and see how they perform. So on the x-axis, we have the amount of data we return in terms of percentages. So on the extreme of the x-axis, we have all the data retained, and we observe that pretty much every method scores around the same amount. But as we keep filtering data out with respect to different techniques, we observe that ensembles of variational methods perform significantly better than the naive random filtering approach or purely deterministic approach that don't capture epistemic uncertainty. In the interest of time, I will just present some other results on training on a data set and then try stuff on different modalities. Thank you very much. So you can find this work online on BDL benchmarks from Oatmeal. Thank you.
Hi, so this is joint work with Mika Livni, who unfortunately couldn't be here today, and David Fleet. This is MIME, the Mutual Information Machine. So MIME is a variational autoencoding framework, and it's designed around three principles. One, symmetry, which means we want to have a consistent encoder and decoder that model the same joint distribution, high mutual information, and low marginal entropy. The divergence is very much related to adversarially learned inference or BIGANs, if you're familiar with those. We also, divergence in our case is the JSD as well, or Jensen-Chan divergence. But unlike those that optimize it adversarially, we bound it and optimize it with gradients and reparameterization. So in practice, we find that this is quite robust against posterior collapse. And this has allowed us to apply this model to domains like text, where fairly small models perform competitively, at least in terms of perplexity, with more complicated large models. Thank you.
Hi everyone. Today I'm going to present you this paper, which is a joint collaboration with Sebastian Marmen and my supervisor, Professor Maurizio Filippone. The question that we are trying to address with this paper is whether we can design a better and more efficient parameterization of variational posterior, both in terms of space and time complexity, but also in terms of the richness of this variational distribution that we can model. So to try to answer to this question, we propose to parameterize the variational posterior by means of structure decomposition based on matrix random theory. So in the paper, we have some application on Bayesian deep neural networks and Gaussian processes with random feature expansion. And I'm going to invite you to check the paper, or even better, check our poster later. Thank you.
Hi, everyone. This is work jointly done with Sumit Gaisas, DJ, and Pushmit Kohli. The main idea is learning representation agnostic to a downstream task, and then using these representations in various applications and trying to ensure that we have certain properties. So, for instance, if we want to use, in this particular work, a variational autoencoder, A representation learned by a variational encoder, as shown in this particular picture, can maybe represent some aspects of an image quite well. But if we introduce a small perturbation to this particular image, the actually representation can render a completely different image with different properties. So this has the consequence that the learned representation would not be robust if it will be used in some kind of a classification task. What we have done is we enhance the the encoder structure using a simple coupling method, and then when we derive the variational method, we derived a new objective function which has 3 terms: the data fidelity, the prior fidelity, and interestingly, a smoothness term, which can be interpreted as an entropy regularized Wasserstein distance, which pops up directly from the analysis. If you are more interested into this line of work and how it is related to disentangled representations or GANs, please come to poster number 52.
Hi, everyone. I'm Christy, and our paper is called Meta-Amortized Variational Inference and Learning. This is joint work with some really cool folks at Stanford, Mike Wu, Noah Goodman, and my advisor, Stefano Erman. So the question that we want to address is, how can we learn good representations for unseen distributions at test time that have some shared structure with the ones that we've seen during training? So our approach is to learn a generative model that uses a meta-inference algorithm that amortizes computation not over just one data set, but over multiple related data sets. So what that means in practice is that we're going to have a shared meta-inference network that takes in 2 inputs: empirical samples from the marginal distributions that we care about, as well as a query point. And this mapping is going to give us back an approximate posterior distribution that we can then use to do inference for our data point X. And the representations that we learn in this way give us good performance on downstream tasks such as clustering and classification. So for more details, please come check out our poster later today. Thanks.
Okay. Hi, everyone. First, I would like to give credit to the first author of this work, which is Agostinos Christiadi, and our supervisor, Asya Fischer. To motivate the idea which led us to compound density networks, we start by looking at the following predictive distribution. This function can be interpreted in different ways. In the context of Bayesian neural networks, where Q from theta is the approximate posterior, or in the context of MC dropout, where Q theta is the dropout probability. Where Bayesian neural networks are mostly trained with variational inference, MC dropout uses the maximum likelihood principle. In our work, we now introduce an input dependency into the distribution over theta. This can again be modeled with variational inference, and then we interpret it as an amortized Bayesian neural network, or we can train it directly via maximum likelihood, resulting in a continuous analog to mixture density models, which we therefore call compound density networks. Interestingly, compound density networks provide the best performance, well, at least in our experiments. I'm happy to talk to you about this approach during the poster session. Yeah, thank you. Great.
Hello, I'm Timon. This is joint work at Nascence with Jonathan Maschi, Jürgen Schmidhuber, and Christian Ossendorfer. I'm Timon. So neural processes basically model a distribution over functions in latent space. They're not designed to capture dynamics of changing parameter distributions. So we extend neural processes through recurrent neural processes, a family of conditional state space models. So in the image, you see that we introduce a hierarchy of neural processes. There is a temporal neural process and a spatial neural process. Basically, we are modeling the state space with a hierarchy of neural processes, where we introduce different dependencies. In our experiments, we are interested in the sequential prediction setting. We encode subsequences of our sequential data to infer a temporal neural process. We demonstrate that this temporal neural process benefits the predictive performance on real-world time series data and nonlinear system identification. If you want to know more about the details, please check us out at our poster. It's in the back on the left. Thank you.
This is joint work with, I'm Jonathan, this is joint work with Mark Gustine. I'm presenting work on hierarchical pack Bayes via deep probabilistic programs. The prior and posterior for pack Bayes bounds can be naturally expressed as deep probabilistic programs. And moreover, hyperpriors and hyperposteriors in this framework correspond to higher order programs. So we use pack Bayes bounds as objectives to train deep probabilistic programs for transfer and meta-learning. And we apply variational techniques to derive valid modified pack Bayes bounds, which we show can be efficiently optimized. So in this framework, we develop a probabilistic type system, which we show allows deep probabilistic programs and modified bounds to be compactly expressed. So on this slide, I've just shown some of the notation that we developed for the probabilistic type system, which incorporates lambda expressions, probabilistic lambda expressions, and a notion of probabilistic reduction as well. So we demonstrate using this approach that we can perform improved transfer and meta-learning on synthetic and genomics data using deep probabilistic program-based hierarchical priors and posteriors. So for more information, please visit me at poster 74.
Hi everyone, I'm Richie Gao. This is a joint work with Eric Kinjip, Jin Xu, Andrew Dai, Dirk Kingma, and Yingnian Wu. A deep EBM is in the form of a Gibbs distribution where F is a neural network. So using noise contrastive estimation, we can turn the learning of EBM to a logistic regression problem by introducing another noise distribution Q. For efficient learning, Q should be close to data distribution, which is usually not true for high-dimensional data. So we propose to transform the noise distribution by a flow model, which is usually also adaptively updated to become a stronger contrast. Specifically, the EBM and the GLOW model are iteratively updated by minimax of a unified value function. And we show that the update of EBM also corrects the over-dispersion problem of the MLE learning. We demonstrate this method on 2D and image datasets, and we also show the application to semi-supervised learning with competitive results to SOTA. Welcome to our poster for more details. Thank you.
Hi. My name's Aiden Gomez. I'm presenting this on behalf of Tim, the first author, who couldn't be here today. So the purpose of the work is to evaluate how we can use typical measures of uncertainty to detect out-of-distribution data. What we do is we translate from German to English and from Dutch to English and see if we can distinguish a model that was trained on German to English, the English sentences that were sourced from Dutch. What we find is that the typical methods like Monte Carlo dropout don't actually effectively separate. Their uncertainty measures don't really partition the data in the way that we like. And we develop a different measure based on the blue score that seems to really quite effectively separate and achieves
almost optimal performance. You can ask me more at the poster session. Thank you.
Hi everyone, this is joint work with my fantastic authors Alexander Lezhov, Dmitry Molchanov, and Dmitry Vetrov. Uncertainty estimation has become a widely used benchmark for assessing the quality of Bayesian deep neural networks and especially ensembling techniques. And today we have a lot of methods for building ensembles and a lot of metrics for uncertainty estimation. And the question is, are these popular metrics actually the right choice for assessing the uncertainty? And the answer is actually no. All of these listed metrics have pitfalls, and these pitfalls may result in incorrect evaluation. The good news is that some of these metrics can be fixed. We use these fixed metrics to evaluate modern ensembling techniques. And most of the ensembling techniques appear to be fairly inefficient during inference and results in just a few independently trained networks, like ensemble of few independently trained networks. Want to discuss these results? Come to our poster.
Hi, everyone. This is joint work with Alexander Turenin, Katja Hoffman, and Mark Dysenroth, and I'm Steindor. So variational integrator networks are a class of network architectures with built-in physics and geometry, the motivation being sort of improving generalization, data efficiency, and interpretability when you're modeling physical systems. Technically speaking, they are symplectic and momentum preserving, and you can do things like define networks with Newtonian physics encoded. And you can use these to learn, obviously, from noisy state observations, but you can also encode this in something like a VAE to learn physically meaningful embeddings from pixel observations. If you're interested in this, please come see the poster. Thanks.
Hello, everyone. I'm Roman, and I'm presenting a software library for working with infinite width neural networks, neural tensions. So as Alex presented this morning, under certain conditions, Bayesian and gradient descent networks are Gaussian processes in the infinite width limit. And these are both promising machine learning models, but also useful tools to gain insight into deep learning. However, there are no software libraries for working with these networks, and each kernel for any particular architecture has to be derived from scratch and implemented. So this is a significant mathematical and engineering challenge. To address this, we are releasing a software library called Neural Tensions. With Neural Tensions, you can define your neural network as usual by stacking a bunch of layers together, and then get both the finite and infinite width models simultaneously with no extra code or mental overhead. Once you've defined your model, you can then run fully Bayesian inference or gradient descent on the infinite model and get your test set predictions in closed form along with the uncertainty estimations. There are many more features to the library, so if you're interested, please check out our website and the poster of the session. Thank you.
Hello, my name is Kirill, and this is a joint work with Artem Gadetsky, Christopher Robinson, Navi Quadranta, and Dmitry Vetrov. In our work, we propose low variance gradient estimates for a distribution over permutations. So permutations naturally occur in multiple machine learning setups, for example, in information retrieval, in combinatorial optimization, causal inference, and so on. And to solve all these tasks, we may need probabilistic models with latent permutations. And the Plackett-Luce distribution is a simple distribution over permutations. And for those tasks, for approximate inference or for variational optimization, we may need to optimize an expectation over this distribution with respect to parameters of the distribution. And how would we do this in the case of Plackett-Luce distribution? Well, a way to go is to use stochastic gradient descent, but to use it effectively, we need low variance gradient estimates. Relax proposes a general solution which is applicable to arbitrary function. However, they assume that the distribution is categorical. And in our work, we extend Relax to the case of the plugget-loose distribution. For more details, please come by our poster. Thank you.
Hello, I'm Eric, and this is joint work with my supervisor Miguel Hernandez-Lobato from Cambridge. And the problem we tackle is out-of-distribution detection. So given a test input x, we want to check if x comes from the training data distribution or a different distribution. And one simple way of doing that would be to train a VAE using maximum likelihood and then to estimate the log likelihood that the VAE gives to the input x. But it has been shown that this doesn't work to detect out-of-distribution inputs. So what we do instead is we estimate a posterior distribution over the parameters of the VAE. So we sample from the VAE parameters using MCMC, effectively resulting in an ensemble of VAEs, as you can see on the right. And then what we do instead is for each of the models in the ensemble, we compute the log likelihood estimate, and then we quantify the disagreement between the likelihoods. So essentially the idea is if the VAEs agree in the likelihoods, or if there's a low variation, then we likely have an in-distribution input. And on the other hand, if the VAEs disagree, so if they produce very diverse likelihood estimates, then we likely have an out-of-distribution input. And it turns out that this works quite well in practice on some data sets. So on the left side, you see the likelihood estimate, which doesn't work well because the scores overlap for in-distribution and out-of-distribution inputs. And in contrast, our score can clearly separate in-distribution from out-of-distribution inputs. So if you want to know more, come to our poster. Thanks a lot for your attention.
We'll now have our first poster session of the day and reconvene at 10:30 for another invited talk.